Hello, I'm Cameron Norris, and this is the final project for the class EEDG 6370 offered at UTD in the fall of 2024. So the goal of this project is basically to just take these three BMP files and run them through a Sobel filter for edge detection. And we're going to do that both on the hard processor in the DE1 SoC board, and then we're also going to hardware accelerate that in the FPGA fabric, and we're going to compare the results between the two. So to start off, I'm going to go over the hard processing results that I have. So what you'll see here is I have FPGA black, white, HPS black and white. The white version produces a mostly white image with the edges coming out black, and the HPS black and the FPGA black are a mostly black image with the edges coming out white. So we'll look at the HPS white version, and so we're going to look at this Sobel C file. So in this file you can see that we include a few headers, and then right here you can see that we use if-defs to define the parameters for the image. So we have the bytes per pixel, the columns, the rows, and then which image we're going to use, and then what the output image will be called. And then after that we define the size of the buffer is going to be 3, so that's going to be a 3x3 matrix, which is right here in this unsigned character. The line buffer, that's the 3x3 matrix that's going to be filtered. And this input row is what gets shifted into this filter. And then the output row is the result of the filter. So now we'll look at the filter itself. And so I actually changed a lot of this code. So what happens in this little bit of code right here is this is shifting the data into the buffer. So the data will be shifted in the X direction. So X0 will go to X1, X1 will go to X2, and then X0 will receive the input row. Other than the shifting, this is the actual Sobel filter. So we have a few variables right here. So these are the matrices that we use to multiply against the line buffer. So right here you can actually see the convolution step where we take the line buffer and we multiply it by these matrices, and then we sum the results in the X and Y directions. And then in this step right here, we take the absolute value of the X, and then we take the absolute value of the Y, and then we constrain it to an 8-bit number. And then right here, we sum the two of the sum of X and the sum of Y into one sum. And then we clamp that down to 255. And then the output is 255 minus the sum. So for the black version, we don't subtract the sum from 255. We just give the sum. So moving on, we have a provided code that will unpack and pack the bitmap. This will open the bitmap and allow us to get all the data out of it. And all of this code was provided, so I'm not really going to go over it. So now you can see in the main that we start by taking the time, because we want to compare how long it takes on the HPS versus the accelerated on the fabric version. And then we have a print statement saying what image is going to be filtered. And then we create this unsigned character pointer TK, and I believe this is where the output image gets stored. And then right here you can see some objects for storing the bitmap header. And then right here you can see where we are going to store the bitmap data and then the output image data. And right here you can see we allocate the memory for the final data. And then we load the data using the load bitmap file function. So right here you can see how we traverse through the image and send that into the filter. So basically we just iterate through the different colors, and then we iterate through the rows. And if it's the first line, then I shift in an empty row, a row of just zeros. And then we iterate through the columns in the image. And if we're on the first row, then we set the input row, the top of the input row to 0, or otherwise we access the correct bit in the bitmap. And then we set the middle index, so this is the actual one that's being filtered. The other two are the surrounding. And then If it's the last row, we'll set the input row 2 to be 0, or otherwise we take the pixel below the one that we're trying to filter. And then after I set the input data, then I shift the buffer. So now the buffer has a row of zeros and a row of data. And if this is the first time through, then we stop there and we will carry on later. So we go back and we get the next row of inputs. And then on the second time through, we shift in data. So we have a row of 0 and 2 rows of data. And then we perform the Sobel filtering on that'll get the result for the first set of data that we sent out. And right here, we take that data that we just got out of the Sobel filter and we store that in the bitmap final image. And then after we iterate through all of the columns, then we have another padding of zeros to send in. So we set the inputs to 0, and then we shift in that 0, and then we perform the Sobel filtering to get the last bit in this row. And then we store the last bit into the column, and we go back through, and now we do another row. So this time, since we already just shifted in a row of zeros, we're not going to shift in another row of zeros. And now that I'm actually going through this, I just realized that we actually only need to do this for the first K byte, so we don't even need this to be for each row. So let's actually change that. So if first, this will happen here, and we'll set the bool out here. And then let's line this up properly. So this change will really cause no difference in the output image. It'll just save a couple clock cycles. So after filtering, we just kind of get some info about the bitmap, and then we create some memory space for TK right here. And then we open a file, which will be the image out, and then we write the bitmap header info into the file, and then we iterate through and write all of the pixels into the file, and then we close the new image file, and then right here we get the time of day, and we print out how much time has passed. And that's basically it for the HPS version. So let's save this with the new changes. And I'm going to go quickly modify the black version. So let's go to the black, Sobel C. You'll see that this image or this file is basically the exact same. The only difference is right here where I said the sum is different. And so the changes have now been applied to both of these. And while I'm at it, I might as well change the FPGA versions, and I will show you that code as well. So now I've opened both of the FPGA versions. It's actually the same code. The only difference will be in the FPGA implementation itself. So up here we have some more includes because we have to include stuff related to the communication between the fabric and the HPS. And then right here we have to define some register bases and span and a mask for the hardware registers. And then we have the same definitions right here for the image and resolution. And all of this is the same, or getting the bitmaps into the program. So the first change comes after all that bitmap stuff, where I have a couple functions for combining characters into 32-bit data so I can send it into the FPGA over the AXI interface. And then down in main, I have to define a few more things. So I have to set some virtual base, a bunch of other stuff related to the hardware. So you can see the first real difference right here in the main, where we have to set up the memory for the device. And then we have to set up the address for the IP that will handle the Sobel filtering. And then here you can see that we have some stuff related to the filtering. So we have 4 inputs, and then we have input data and output data. and we have the results. And so I'm going to make the change right here where we'll move this bool outside. And the biggest difference between my HPS implementation and my FPGA implementation is in the FPGA implementation, I'm actually filtering two rows of data at the same time. So since I have a 32-bit bus to send data over, and one Sobel filter only requires 3 bytes, I figure I might as well send over the 4th and then just filter them at the same time. And I was actually trying to use the 64-bit and 128-bit AXI interfaces, but I could not get them to function properly while I was testing. So I'm stuck with the 32-bit AXI interface. So, and if I had the 64-bit interface working, I could do 6 filters at the same time. And if I had the 128-bit bus, I'd be able to do 14 filters at the same time. But since I don't have access to that, I'm stuck with only 2. So to actually go over the filter itself, so I actually iterate over the bytes per pixel, just as with the HPS implementation. And then the first time through, I'll send in a 0 into the device. And then I iterate over the rows. And what you can see right here is I actually iterate over 2 rows at a time. And then right here, you can see this bool, the second. And what this bool is for is actually I'm going to do 2 writes for every read that I have, because the output is 8 bits and I have 2 outputs per write. So over a 32-bit address, I can fit 2 of those. So every read operation, I'm going to be getting 4 pixels in the image. So then after I declare this bool, I iterate over the columns. And just like with the HPS code, if I'm on row 0, then I set the top input to 0, and then otherwise I set it to the proper pixel. Input 1 will just always be a pixel. Input 2, in this case, will always be a pixel. And then I have an input 4, which will either be 0 or a pixel. And the reason I can do this is because all of these images are actually going to be an even number of columns. If we had an image with an odd number of columns, I'd actually have to change this to where this input could possibly be a 0. So after I set the character inputs, I combine them into a 32-bit variable, and then I send this over the AXI interface using this alt-right word. And this actually comes from the SoCal library up here, socal/socal.h, and this gets sent to the Sobel address. Now if it's the first time through, just like in the HPS, then after that I'll just skip over. And otherwise, if it's the 3rd time or the 5th time through, then I will actually take the output data. So I'll read using this alt-read word, and that'll get sent into the out data. And then I'll take this out data and I'll split it into characters. So I have results 3, 2, 1, and 0. And then I take these results and assign these to the proper pixel in the bitmap final image. So if we were to look at this as if it was a 4-pixel image, result 0 would go to the top left, result 2 would go to the top right, result 1 would go to the bottom left, and then result 3 would go to the bottom right. And then I toggle the second bool, so the next time it goes through, it'll come right here. Now after it iterates through all of the columns, I will do one final write, which will be a 0 input column, and then I will read the data, and then I will assign it to the proper bits just as before. And then same with the HPS, I just get some of the bitmap data, and then I write that out to the file, and then I write the pixels out to the file. And then down here, we free up the bitmap final image, and then we unmap the memory, and we finally get the elapsed time and print that out. And now that we know how the C code works, I'm going to start going through the FPGA code. And for that, I'm going to open up No Machine. To do this, you actually need to be on the VPN for the school. So you can see right here I'm connected to the UTD Global VPN. And I will go to the terminal. Now let me navigate to the HPS file. And then I will go into the project directory. And then here you can see I have two different projects going on. So I have FPGA RTL2, and I believe this is the white version, and I have FPGA RTL, which is, I believe, the black version. And we are just going to open up one of them because they're basically the exact same. So I'm going to go to the FPGA RTL folder, and I'm going to type in Quartus ampersand to launch Quartus. So now I'm going to open the project, and now that I'm in this project, you can see there's this GHRD top, and under this is the SoC system. Now this is what we're actually going to care about. And now that we're looking at the HPS system, what you can see is I actually have this AXI memory map slave 0, and this is my custom device. So you can see that there's this Altera AXI 4 Lite interface that connects to the H2F lightweight AXI master. And then we have a clock and a reset signal going into that. So I'm going to open up this AXI memory map slave. And you can see the different ports right here on the slave. And then you can see it comes from this AXI mm slave.v file. And then you can see that it has some parameters. So it's a 32-bit data width and a 6-bit address width. And then right here you can see that the interface is the AXI 4 Lite slave, and you can see all the different signals, and you can see that the clock and the reset are associated. Now let me open up the file and show you what that's like. And so in here you can see that we define the interface for the AXI memory map slave, and then we have a bunch of registers for the AXI memory map. And then right here what you can see is we have some stuff related to the Sobel filtering. So we have an X and Y matrix. Then we have the P matrix, which is the pixel matrix. We have some matrices for the X results, the Y results, the X result, Y result. It's a little confusing, I know, but it's how I name them. So, and then I have a result NT. The NT was kind of meant to mean not truncated. And then we have the final result right here. And a lot of these are signed registers. And then we have a signed wire right here. And with this P matrix right here, you can actually see that it's two different matrices, two 3x3 arrays. And then right here, the X results, it's also two different 3x3 arrays, and the Y results are the same. And then I go down to 3-bit or 3x1 arrays for the X result and Y result. And then finally, I just have a 31-bit value for the result NT, and the final result is the when I truncate it down to a character. And right here, we have a bunch of logic for the AXI interface. So this is where it starts to get interesting. So I have a slave register 0, so I actually extended this to be a 3x1 array. So slave reg 00 gets the input data from the AXI bridge. Slave reg 01 takes the value of slave reg 00, and then slave reg 02 takes the value of slave reg 01. And then also in this block right here, I set the output register to shift as well. And this is to handle returning two different results at the same time. So the output register, the top 16 bits, are used to store the most recent result, and this just gets updated every clock cycle. And then the bottom 15 bits hold the last results. And then down here you can see that we assign the AXI read data to just be the registered data out. And then down here you can see the Sobel filtering. So we assign the X and Y matrices to hold the proper filter values. And then right here you can see that we assign the P matrix to hold the proper values from the input. And then in the same generate statement, we set the result nt to be the X result and Y result 2. And then we set the result to be the 8-bit truncation of the result nt. So for a lot of the filtering, we register it so that it can meet the 50 megahertz clock speed. So you can see into result X and Y, it is the addition of all the X results and Y results matrix indexes. So then in this code right here, you can see that we take the absolute value of the result, and then we clamp the result down to an 8-bit value. And then right here, you can see this is actually where the matrix multiplication happens. And real quick, I'll show you the difference between this version and the other version. And the only difference in this code is right here. You can see this result SB, so result subtraction. And then down here, what you can see is the result Z takes 255 minus result SB, and result SB is the clamped down version of result NT. And that's the only difference between the code. So now to go back to Cordis. So if you update the file right here, you would hit finish, you would hit save, and then once this is done, you hit close, and you hit generate HDL, and you generate it. And once it's done generating, we'll hit close, and we'll hit finish. And then back in Cordis Prime, you'll see that the compilation will, if it's actually updated anything, then the compilation will change, so you'll have to recompile it. But since it's not required at the moment, I'm not going to do that. So one other thing I want to show you real quick is actually in the files. If you look at theghard top, I actually set the hex values to read out 1, 2, 3, 4, 5, 6. And this will show you that you actually have the FPGA program with the proper SOF file. I did not change this between the black and the white versions though. I probably should have, but I didn't. And now that I'm out of Cordis, I'm going to just go back to the top. And what I'll actually do at this point is I would run, I believe, the zip, and then I would type something like proj black 2.zip, and then I would type in FPGA -RTO, and what this will do is this will zip up FPGA RTO into the project black 2.zip. So actually I had to change it real quick right there. I had to add the -R because otherwise it would not add any files to it. So you can see that we just produced this proj black 2.zip, but I am not going to use that because I already have the proj black and the proj white. So let me just delete that because I don't need it. And so right now I'm going to change this, or I'm going to transfer these zip files over to my Windows computer. So I'm going to take this proj black zip and save it right here. And then I'm going to do the same for the proj white zip. And now that these zip folders are transferred over, I do not need to use No Machine anymore. So let me just close out of it. And so now we're back on Windows. And let me go to the project folder. I'm going to unzip these. So now I've unzipped these proj white and proj black zip, and I'm actually going to delete these. And now let me go to Proj Black, and I'm gonna just rip this out and put it right here. And then I will do the same for Proj White. Just rip that out. And then I'll just get rid of those folders to get rid of any confusion. And so now in this project folder right here, you can see we have FPGA black, FPGA white, HPS black, and HPS white. So at this point, we're going to have to use the embedded command shell. So you can see it's under this PC SSD1, which is my C drive, and then Intel FPGA 20.1 embedded, and I'll use this embedded command shell.bat to launch that. And so real quick, I'm going to show you a little commands file that I set up. So this has some useful commands. And so I'm going to run these three right here. So what this does is this adds a Quartus SOPC builder bin to the path. And this provides an alias for me to just quickly get everything in a directory, and then this will see to the project for me, so it's a little easier. So I'm gonna just run that, and now you can see everything is as it should be. And so now I'm gonna go into project. We'll start off with the HPS white. So now that I'm in HPS white, we'll look at the make file real quick so I can show you what that does. So I just opened the make files for the HPS version and for the FPGA version, and there are only a few differences. So in the HPS version, we create these Sobel exe files, whereas over here, we just call them Sobel FPGA. We don't have any extension. And then all this is the same. And then down here, it's basically the same, just with a few differences. So on the HPS version, we take the Sobel C, make a Sobel O, and then on the FPGA version, we take a main C and create a main O, and then we also have main HD, main boat, and then Sobel HD and Sobel boat. But basically both of these files just create the executable that we need to run on the processor. And so now that I gave you a quick look at that, we'll just close out because we really don't need this right now. So now in the HPS white folder, let me go back there over here so you can see everything happening. So we're in the HPS white and HPS white right here. So we'll just run a make. And this will create the project to use the Lena image. And then we'll do a make boat. And this will create the executable for running with the boat image. And then we'll do a make res HD. And finally, this creates the executable for using the Batman and Joker image. And so we're just going to do this for the other HPS as well, the HPS black. So now we're in the HPS black directory, and we're just going to run those same commands. So make boat, and make res HD. And now I'm going to show you what we do for the FPGAs. So we go back, and then I will go into FPGA white, and then we'll go into the FPGA RTL. And then in here, what we'll do is run this generate script, which will generate the header file that we need. And so now we've generated the header file, and I'll copy this over. So I'll just do cp hps_0.h, and I'll copy this over to the HPS folder. And then I will go to the HPS folder, And then I will run the same thing, so I'll do main, or no, my bad, make. I'll do make boat. And I will do make res HD. And then I'll do the same thing for the HPS black, or my bad, the FPGA black. And what you'll see is that now all of these have the proper files. And so now what I'm going to have to do is set up the FPGA. So now I'm going to start up the FPGA. So let me open TerraTerm. This is how we're going to connect to the FPGA. We'll use COM port 3, hit OK. And then we'll set up the serial port to use the 115200 new setting. And then we'll turn on the FPGA and we'll actually see the whole startup process. Now you can see that the FPGA is actually started up, so we'll do root. And then, so now we're in the FPGA. Now let me set a password. And we'll just set it as terasic and terasic. So now we've set up a password, and if you look at this, the notes, you have to run this UDHCPC and ifconfig, so this will give me a IP address that I can talk to. UDHCPC, and then ifconfig, and you can see the IP address that I'm going to need to use to communicate with the FPGA is this 192.168.68.77. And then I'm going to use that with this root command to copy files over. So on the FPGA, let me set an alias. Alias L equals ls minus L. So now you can see that in the root directory we have nothing. So over here, I'm in the FPGA black, the HPSC directory under FPGA black, and you can see we have some files that we need to take over. So we're gonna run this scp command to copy those files over to the FPGA. So I'm gonna copy everything named Sobel star, which is the wildcard, to home root, and then I will make a new directory. Just to be safe, I'll do make directory, we'll do FPGA underscore black. So now we have some directories and we're going to copy stuff over there. So we will copy this to the FPGA underscore black directory. And we have to type yes, and then we have to type the password, which is terasic, and it copies the files over. And we're going to go into the FPGA black folder, and we should see those files now. So you can see we have the Sobel FPGA, Sobel FPGA boat, and Sobel FPGA HD. And so now we want to do the same thing for all of the other directories. So now I'm going to do the same thing for the FPGA white. And then I'm going to do it for the HPS black. Now over here, instead of copying over all these Sobel files, I'll copy over the exe files. And then I'm gonna do the same thing. I realized I just copied those over to the wrong place, but that's really not an issue. So let's go into the FPGA white, and we'll see that I just copied those over to the wrong place. And so what I'm gonna do is I'm gonna move these. So I'm gonna do move star.exe, and I'm gonna take it back over to the HPS black. So now you can see that we moved those over to the HPS black and all is well. Now I'm gonna navigate over to the HPS white. And we're gonna run that same copy command, but HPS white. So now I have all the executable files copied over, and what we actually need to do right now is copy over the images that we need to use. So I'll do cd into the I believe it was this the Sobel _ source file. So now I'm gonna do a secure copy of the BMP files over to the Terasic FPGA, and we'll do SCP BMP, and we'll just do it into HPS white for now. And then over here, I'll go into the HPS whites, and I'll just CP all of these BMP files over to the other directories. So all of these BMP files are going to be in all of those directories. And now at this point, we're actually ready to run the HPS white and black. So let me run those right now. So first I'll run the black. So we'll do cd HPS black. And then here, what I'm just gonna do is I'm gonna type sobel.exe or period slash sobel.exe, and that will execute, and it will run in 0.363708 seconds, and it will produce the Lena 512_out.bmp. So now I'm gonna run Sobel boat.exe. This will run in 0.363332 seconds, and this will produce the boat out BMP file, and then we will do the same thing for the HD file, and this is going to take a lot longer. And now you can see that the HD file was computed in about 25 seconds, so 25.831198 seconds, and that produces the Batman Joker _out.bmp. And now I'm going to go over to the HPS white, and I'm gonna run all of those commands again. So I'll just run the Sobel exe, that completed in 0.364066 seconds. I'm going to do the Sobel boat, which completed in 0.364438 seconds. Now I'm going to do the Sobel HD. And the Sobel HD completed in 25.886356 seconds. And you can see that all of the output images were produced. So now I'm actually going to secure copy these over to my Windows PC and we'll see the results. Let me open the HPS white area. So we're going to copy the output BMP files to this directory. And what you can see is we're going to cd out, we're going to go into project, and then we're going to go into HPS white. You can see there are no BMP files in there right now. So we're going to do a secure copy. From root HPS white. Then we're going to copy over all of the out_out.bmp files. And then we're going to do it into this directory. And we'll type yes, and we'll type terasic. And now it'll copy these files over to the Windows PC. And now you can see that these BMP files now exist on this computer. And we'll look at those. And this is the Batman Joker BMP. And then we can see the boat BMP, boat out BMP, and the Lena out BMP for the white version. And I want to do the same thing for the black version. So we'll do /HPS_black, and we will do from the black directory right here, and we'll go over there so you can see that copy happening. So now you can see that these images were copied over, and this is what it looks like now on the HPS black. And so now we need to do all this for the FPGA implementations. So I'm going to go over to the FPGA white area. And you can see we have the BMPs and we have the executables. But what we actually need to do first is we need to flash the design onto the FPGA. Let's open the programmer instead. So over here I have the programmer, and we're going to do auto detect on the chain. We're going to use the 5C SEMA5. And we're going to select the SOF file that we're going to program. So we'll go to my computer, we'll go to SSHD, school, UTD, 6370, project, FPGA white, because we're looking at the white version, and then this socsystem.sof file. And this is going to be programmed onto the FPGA, but I actually want to show you that happening, so let me enable my webcam. So right now you can see my webcam, and I'm going to move my webcam so you can see the FPGA. So right now you can see kind of that those are all set to 8888. And now I'm going to flash the FPGA. So you can see that the FPGA was now programmed. And you can see that there's 6, 5, 4, 3, 2, and 1. So now the FPGA has properly been programmed to do the white Sobel filter. And so now that the FPGA has been programmed, we're going to just run this. So we're going to run the normal Sobel FPGA. So we'll just type ./Sobel FPGA. And you can see that it runs in 0.112481. So it's about a third of the time of the HPS version. And so we're going to run the boat. And that runs in 0.112737 seconds. And now we're going to run the Sobel HD. And the Sobel HD version ran in 7.903333 seconds. And all these times are much faster. They're about 3 times faster than the HPS version. And now what I'm going to do is I'm going to actually program it to run the HPS Black. So let me go to the FPGA Black. So we'll go to FPGA Black. And right here, we're going to go into this area and program it for the black. So now the FPGA is programmed, and what we're going to do is we are going to now run the same as with the FPGA white. So we'll do ./Sobel FPGA, which finished in 0.112628 seconds. Then we'll do the boat, which ran in 0.112537 seconds. And then we'll do the HD. And the HD ran in 7.904189 seconds. And you can see it produced the output BMP files. And so what we're going to do now is we're going to copy these over just like we did with the HPS. So right now we're in the FPGA white directory, and I'm going to run the SCP, but we need to get from the FPGA directory. Let's do FPGA white. And we'll just copy right here. So we're copying from home root FPGA white. We're taking all the out_out.bmp files, and we're copying them to the FPGA white directory. So let me run this. Yes. Terasic. I forgot to show you, my bad. FPGA white. So you can see that these, if I go to the details, properties, were created December 12th, 2024 at 1:34 a.m. and it just turned 1:35. And then I will do the same for the FPGA black. So let me just go up and we'll do black, and we'll do this to the FPGA black. So we're copying the FPGA black out BMP files to the FPGA black directory. Let me show that copy happening. So you can see there's nothing right now. And we'll do the secure copy. I'll type yes, and I'll type Terasic. And now you can see that the files are being copied over to the Windows platform. And now you can see that the files are copied over. And we'll actually look at these and compare them. So first up is the Batman and Joker FPGA image. And then we can see the boat BMP produced by the FPGA. And then the Lena BMP. And these are the black versions, and now I'll show you the white versions. The Batman and Joker, the boat, and Lena. So now I'm going to show you side by side the comparison between the FPGA and the HPS. So these are the two different, one of them is from the HPS and one of them is from the FPGA. I'm actually not certain which is which at the moment, but they look pretty much identical to me. And then we'll show the boat. And I can try to zoom in a little bit. We'll do 250% on both of these. And to me, they look basically the exact same. And we'll do the same for Lena. And we'll zoom into 250%. And again, they look exactly the same to me. So now we'll look at the black images. So we'll open up the FPGA black first. I'm going to put the FPGA black on the left side. And then let me open up the HPS black. And I'll put this on the right side. So now we know the HPS is on the right side and the FPGA is on the left side. And so looking at the Batman and Joker image, I see no differences. I really do not. Now I'm going to go over to the boat and zoom into 250%. And again, they look pretty much identical. And so now I'm going to go to the Lena images. Zoom into 250%. And to me, they look exactly the same. So my FPGA implementation, which runs 3 times faster than the HPS implementation, produces identical, if not nearly identical, if not identical images to the HPS only version. And so now what I'm going to do is I'm going to take this out and I'm going to zip up this folder. And that's what I'm going to submit. So with that, what I've shown you is I've taken a Sobel filter that runs on the HPS. I've created a version of that to run on the fabric of the FPGA. Then I've created a program that will run software on the HPS to communicate with the fabric on the FPGA and transform a BMP into an edge detected BMP that runs about 3 times faster than the same process only running on the HPS. And with that, I will call it a day. Thank you for watching. Hello, so I'm actually coming back the next day for a correction, and what this correction is around is the use of these bools, the first, and now I have a new bool called first column. So it is true that for the first ever input into the filter, I need to do a single shift n of zeros that I don't need to replicate due to shifting in at the end of each column a row of zeros, but I actually still have to shift or shift in new data at the beginning of each column without adding that into the pixel map. And even in my original code that I ended up changing during the course of making the video, this was not in the correct position. So now for each row, it'll reset this first column, and so this should fix an issue where it would actually not be placing the pixels in the correct spot, and it would technically on the very left edge not be even, it would be looking at data from the previous row. So anyways, this is has been fixed in both of the HPS builds, and it's also been fixed as seen here in both of the FPGA builds. And now I'm just going to show you the difference in runtime, and also I'm going to show you the images that this creates. Okay, so now I've come back and I've now copied over all the new files with the changes to the C program, and I've copied it over to the FPGA, and you can see that all of them are properly there. Now I'm gonna just do the HPS white first. And I'm gonna execute the Sobel exe. And that ran in 0.409277 seconds. I'm gonna run the Sobel boat exe. And that ran in 0.409008 seconds. And now I'm gonna do the Sobel HD video, or Sobel HD executable. And the Sobel HD executable ran in 26.898697 seconds. Now I'm going to do the HPS black. I'm going to run first the Sobel exe, and it ran in 0.407987 or 982 seconds. And then I'm gonna do the Sobel boat, which ran in 0.408871 seconds. And now finally the Sobel HD. And the Sobel HD ran in 26.840759 seconds. And you can see I've already programmed it with the FPGA black version. So we're going to do the FPGA black now. And first I'm going to do the Sobel FPGA. And that ran in at 0.157840 seconds. And then we'll do the Sobel FPGA boat, which ran in at 0.158012 seconds. And then we'll do the Sobel FPGA HD. And that ran in 8.926877 seconds. And now I'm going to program this with the white version. So it's now programmed with the white version. And we're going to head to that directory. And we're going to run the same executables. So the Lena image ran in 0.158155 seconds. Then we'll do the boat, which ran in 0.157877 seconds. And then we'll do the HD. And the HD image ran in 8.925396 seconds. And so now we're going to copy all these back over to the Windows folder, and we're going to look at them. Alright, so now I've come back after copying all the images over into the Windows environment, and we'll take a look at the black images from the FPGA. And what I can say is that it looks like it's perfect, and I really don't exactly see a difference between what I have now versus what I had before, but I do know that this is a more correct image than what I had before. So that's the FPGA black. Now the FPGA white. And then we'll look at the HPS black. And then we'll look at the HPS white. And I would say that the difference in the images is very minimal, but it was worth coming back to actually get it to be correct. So thank you for watching. Sorry the video has been very long, but I appreciate your viewership. Thank you.